Okay, perhaps we can begin.
Okay, great. Yeah, I will share my screen.
Yes, so welcome everybody again to the second talk of the day, and we are happy to have Kshitij Gupta from California, and he's going to talk about soft metric fluctuations during inflation. So maybe
Yeah,
I'll send you a reminder when 5 minutes are left.
thank you so much. Thank you also a lot, Dr. Anish Ghoshal, for inviting me to give a talk here. I'm now going to be a fourth year PhD student under Dan at San Diego, and I'll be talking on my work with him on soft metric fluctuations during inflation. So yeah, we can just jump into this. Okay. Um, so just to review the classic picture of inflation that we all have, we can think of inflation as roughly this ball rolling down the hill picture, which all of us have seen before, which really represents a scalar field undergoing quasi-de Sitter space-time expansion. And so yeah, so this is a ball slowly rolling down the hill, and that's how we think of inflation. And after some point, inflation ends, the ball drops down the potential slope, and we enter the reheating phase, and then conventional Big Bang happens. So, really, this ball is a quantum object. So, while it's rolling down the hill, it's also fluctuating. And what we want to do is we want to understand or study these primordial perturbations, which are represented by the quantum fluctuations. So there are multiple gate choices that we can do to understand these perturbations. The one we'll use in this talk is for inflation. You can use the gate choice where the field phi itself is fixed and it has no fluctuations. And if you want to do that, you need to absorb all the perturbations into the metric. So these are, oh, sorry. So these are the zeta perturbations, and these are essentially the curvature perturbations. And when you absorb all the perturbations into the metric, essentially the metric is given by Gij is your scale factor, which is e to the 2 ht for de Sitter h is constant, and times this e to the 2 zeta. Great. So this is the perturbation that we want to focus on for the rest of the talk. And for zeta, we expect it to be time independent on super horizon scales. So this is what we call the conservation of zeta. And this is important because the primordial perturbations generated during inflation then acts as the initial condition for rest of cosmic evolution. So for Big Bang, nucleosynthesis, for radiation-dominated era, matter-dominated era, these modes are constant outside the horizon. And we expect that from the symmetries of zeta. This is because in the soft limit where k tends to 0, we expect that roughly zeta behaves like a constant. That's just because it has no spatial profile. Uh, and if zeta roughly behaves like a constant, all we've done is we've just redefined the scale factor. So we should not have any dynamics in the system. We've just redefined what the background scale factor is. So this kind of seemingly intuitive fact, at least from the symmetries that we expect to hold, is hard to show technically. So zeta is a quantum perturbation, so we want to show this in a quantum calculation. But because of quantum loops, this is technically quite a little challenging to actually prove. So it has been proven to all orders by these authors. But the arguments are diagrammatic in nature and they are long, tedious arguments, and you need to show cancellation between different diagrams to finally prove that zeta is conserved or time independent outside the horizon after you take into account all of the quantum fluctuations. And really, the motivation from this is that if we want to see something that we feel is obvious in a cleaner way, maybe we want to understand the physics better. Uh, so we want to understand the physics of zeta in a better way. And One can ask what the worry is. Why are these calculations hard to do? So very practically, you can try to measure the two-point correlator, or the power spectrum of zeta generated during inflation at some late time boundary, and you can just try to do the ENN calculation, and you can just put in a generic quantum loop and just do the calculation. Now remember that the metric was e to the 2 zeta. So in general, you'll have derivatives of metric in the action. So you'll have a bunch of e to the zetas in the action, and you'll have derivatives of zetas as well in the action. And you'll also have some powers of AHs or A's essentially. So one of the questions, roughly speaking, that can arise is the following. If you have these derivatives of zeta in these quantum loops, can they give rise to any additional time dependence? Can this go as some power of AH so that in the far future, as A is growing, this entire quantity actually starts growing? So that's one question you can have. And the other question you can have is that we have these e to the zetas, and you can expand them, and they have an infinite number of self-contractions. So how do you deal with this object? Um, can all of these infinite self-contractions also give rise to any time dependence on the late future boundary? So this is roughly the technical side of how people want to prove that zeta is time independent. And what makes these calculations even more difficult or confusing is that in de Sitter, we don't have very nice regulators or obviously nice regulators. So usually in QFTs, we choose nice regulators because what they do is they try to keep track of as much of only the physics as possible, and the scheme-dependent things we try to throw away with our regulators. And DimReg often does that for us, at least in textbook QFT, flat spacetime, it works very well. But in de this is not the case, and a lot of the times people end up worrying about what regulators they've used, what schemes they've used, subtracting the divergences properly and carefully to have to show that, for instance, zeta is time independent or to get other results in de Sitter. So let's just quickly review how regulators usually make our lives a lot easier. So let's just do flat space time. Um, so let's consider this loop diagram due to a scalar um, and with an interaction term, which is given by g over lambda to the fourth. So lambda is some energy scale in a EFT, and the coupling is given by partial nu phi whole squared. So if we try to compute this loop, generically we'll get just a d4p over 2 pi to the fourth loop integral. And one way to regulate this would be to use a hard UV cutoff. If we do that, we'll get this answer right here, lambda UV to the fourth over lambda to the fourth. And after we've done the loop calculation and we've gotten this result, it's not obvious if this term gives rise to RG or not. And really, this will be absorbed by a local counter term, so we can introduce a counter term, and after doing the work, we'll see that there's no RG or logs due to this loop integral, but we had to work a little harder outside of just calculating the loop integral. So this is the hard cutoff version, but that is why we often use dimreg, because dimreg actually sets this directly to zero because it's a scaleless integral. So that's one of the advantages. And that makes it obvious that this will not give rise to any RG. We didn't have to introduce counter terms or do any of that stuff. So this is the way in which usually nice regulators work. Um, but in de Sitter, we don't have this. And roughly, even dimreg doesn't work as well in de Sitter because in calculations, we usually have loops of the form some power law of p, but we also have a e to the I pt term because you're calculating the loops at some time, fixed time t, and so you have these exponentials from the oscillating modes. And because of this, p and t scales are intimately coupled, and this essentially also doesn't allow Dirac to work as cleanly as it does in flat spacetime. Okay, so really, the entire motivation for us right now is that we want to understand statements like zeta is time independent in a more direct way. And really, what we also want to do is we want to understand super horizon physics of de Sitter in a more manifest way. So we want to develop techniques to do that. But really, this goes hand in hand with understanding how to regulate loops in a more convenient way as well, so that it makes the technical aspect of handling quantum fluctuations of super horizon modes a lot easier. So that is the big picture motivation for the talk. And for the rest of the talk, we are gonna have two ways of accomplishing this. So to understand the physics better, we'll write down a EFT description for the super horizon modes, which have exited the horizon, and for I guess yeah, super horizon modes, and this will make the IR behavior manifest, and it will also give a convenient way of regulating loops in the IR. And also for the full theory, we will so for modes even inside the horizon and outside the horizon, we will introduce the Mellon representation as another technique for calculating loops in de Sitter in a way that very closely matches dimreg in flat spacetime. And an added advantage is that it is a natural scheme to match onto the EFT when doing loop calculations. So that's roughly the plan for the talk. Okay, so we can jump into the EFT. So what we want to do is we want to construct an EFT for the metric modes zeta, so that we can reproduce the IR behavior and in particular any secular divergences and time dependence. So in generic models, zeta usually propagates with the speed of sound, CS, which is any value less than equal to 1. But for the purposes of our discussion, we can just set CS to 1 because it doesn't change any of the results. We have uh, the generic CS results in our paper, but it will just make the discussion a lot simpler to follow. Okay, so we want to construct an EFT, and so let's try to understand what is the regime of validity of the EFT. So the technical motivation starts with the idea that IR logs that we see, the secular divergences, they're of the form k over AH. So these are the ways you could have time dependence, logs k over AH in de Sitter. And we want to understand this as a statement which is similar to log p square over the cutoff square in flat spacetime, which we get when we do RG in flat spacetime. So just making that analogy, what we want to do is construct an EFT with a cutoff given by lambda co-moving is AH because K is the co-moving momenta. So we want a co-moving cutoff given by AH so that we can reproduce the IR divergence behavior. So physically, a very clear thing is happening. When you have any fluctuations produced in de Sitter, it starts its life in the horizon with k much greater than AH. And as spacetime expands, at some point it crosses the horizon, and then it becomes super horizon mode, where k is much less than AH. So when you generically do any calculation in Decider, you will track the life of the mode from inside the horizon to outside the horizon, and it will run over all of these scales. But the EFT we want to consider will have a cutoff given by AH, and it will only focus on the behavior of modes once they've crossed the horizon, and everything else we are integrating out. So that's the physical picture behind the EFT. And okay, so if we have an EFT, we should define a power counting parameter. So what we will power count, or the small variable which we'll Taylor expand in always, is lambda equals k over ah, or k tau, which we know will be small because we are outside the horizon. So this is the small quantity that controls our theory. And actually, very nicely, this actually already accomplishes our first goal, which is to do loop integrals in a nice fashion. This is because any in calculation that we will see will be of this form again, k to some power, but also with the e to the I k tau. Because k tau is small, we'll always Taylor expand this. So really what we get is powers of k's and taus, and k and tau is now not coupled anymore, essentially. So now we can just integrate this term by term in the same way we do in dimreg, in flat spacetime. And we can, for instance, set them to 0 via scaleless integrals. So this is a great simplification. And so we've understood how to do, at least for this EFT, that the loops will be a lot more convenient. But we also want to write down the theory now and write it in a way so that the effects are obvious just by looking at the action. So we still don't want to do loop calculations to prove that zeta is time independent. We should understand the IR physics just by looking at the action, and the loop calculations should only really be necessary to calculate factors of 2's and pi's. Um, so we should understand the effect of a term just by the action. So the theory that does this is soft de Sitter EFT, which Dan Green and Tim Cohen came up with in 2020. So yeah, so that EFD just focuses on the fluctuations once the modes have exited the horizon, and we will use that to describe these inflation modes as well. Great. So let's jump into soft de Sitter EFT. So so zeta satisfies the UV equations of motion, which is given by this equation. And if we take the long wavelength limit, k to 0, we can identify two degrees of freedom classically. One is a constant, and the other decays as tau cubed because tau is going to 0. Tau is the conformal time, so it's given by 1 over ah. And what we want to do is we want to describe the fluctuations around these classical long wavelength solutions. So right. So this is what we want to do in our EFT. And these are the degrees of freedom. Another way to see the degrees of freedom is that if you just take this equation of motion and you solve it, maybe some of you have seen this before. De Sitter has this solution for the modes. And you can just take the k tau much less than one limit, again, which is the super horizon limit. And you will get that you will have again two degrees of freedom, one which is real and one which is completely imaginary. And you'll call these zeta plus, which is the constant, the leading order constant, and zeta minus, which goes as tau cubed. So this is the growing mode and this is the decaying mode. Good. So, what zeta plus and zeta minus essentially do is they act as scaling operators because they're proportional to powers of k. So as you scale x and k, zeta plus is a constant, so it scales as lambda to the 0, while zeta minus scales as lambda cubed. And so zeta plus scales as k to the 0, zeta minus scales as k cubed. And because zeta plus and zeta minus are expansions in k tau, they they make explicit our intuition of power counting. So now to derive so these are the degrees of freedom that we want to work with in this EFT. And these are the two fields that we want to work with. So to derive the action, we can just expand in the soft limit. So we can just plug zeta as zeta plus tau cubed zeta minus. And from there, we can derive our EFT action. But correcting for slow roll factors, instead of tau cubed, it would just be 3 plus 2 epsilon plus zeta, which is the tilt of the power spectrum. Great. So now we want to write down the action not in terms of zeta plus zeta, but zeta plus and zeta minus. And because we have 2 degrees of freedom, we expect to get a first order equation for zeta plus zeta minus, because we started with 1 degree of freedom and a second order differential equation in zeta. So the action that we get after some algebra is this thing right here. And as we see, it's a first order equation in both zeta plus and zeta minus. And we also see that zeta plus and zeta minus are conjugate momenta of each other from the leading order kinetic term. Um, Also, the EFT will be supplemented by initial conditions, which will describe the statistics of zeta plus and zeta minus at horizon crossing. So, so this part, the EFT itself does not predict. The horizon crossing statistics is given by the UV theory, and it's determined by matching to the UV theory. But right, so with this, we have all the ingredients in our EFT. Now, remember the motivation was to understand the time dependence of zeta after horizon crossing. And because the constant mode was zeta plus, we in the EFT, what we want to do is we want to understand the time dependence of zeta plus. So time dependence is actually in the EFT equivalent to doing an RG analysis. This is because our cutoff is AH, remember? And RG equations are of the form lambda dd lambda of some operator is 0, or the derivative with respect to log of lambda is 0. So because lambda is and a is an exponential in time, the Kalman-Semantic equations essentially become the derivative with respect to time of some operators, uh, is essentially telling us their anomalous scaling dimension is gamma times the operator. So this is a great simplification. We know how to do RG analysis very well from textbook EFTs, and f- so yeah, so in this EFT, the big picture question that we asked to see the time dependence of zeta just becomes a analysis of RG and marginal and relevant and irrelevant operators. So the goal is simple: write down the EFT based on symmetries and power counting, check whether the EFT produces any marginal or relevant terms, and if not, we can make an all-order statement, including loops, about whether zeta is time dependent or not. Okay, so let us quickly understand the interaction terms. In general, because zeta plus and zeta minus are the only 2 degrees of freedom, we can have any powers of them. And we can have the cutoff to the power 3 minus m beta. So the zeta plus scales as k to the beta. Oh, sorry, zeta plus scales as k to the 0. Zeta minus scales as k to the beta. And because the action should be scaleless, we have lambda, which also has some scaling behavior, uh, as literally lambda. So this combines to give you a scaleless quantity. So that's why we need this power of lambda. Um, and the measure also scales. So that's where you get the 3 from. And the units are made by lambda. So zeta plus and zeta minus don't have units. So this makes up all the units. And you can have some additional Wilson coefficient terms which capture slow roll effects because we are really in quasi-de Sitter spacetime. So we can have some ah to the epsilon and ah to the eta terms. So yeah, this is what a generic interaction term will look like. And we want to understand the power counting of this term. So in general, because the zetas give you all the powers of k and the lambdas give you the power of this goes as k over ah to the m beta minus 3, where beta is essentially 3 up to some tilt factors. So, so for m equals 0, this goes as k over ah to the negative 3. So it's a relevant term uh, in the Wilsonian RG language. For m equals 1, this goes as k over ah to the 0, so it's marginal. And for m greater than 1, this is irrelevant. Okay, and remember all the m comes from the factors of zeta minus, which is the decaying mode. So having no decaying mode makes the EFT term relevant, and having one of them makes it marginal. We could also have added spatial and time derivative terms, but they power count as further factors of k over ah, so they are usually more suppressed. So that's why we are not really worried about these terms. Okay, so then the leading order interaction should be the one where we didn't put any zeta minus, as we said, because that is the relevant term. This is the guess, but this turns out to be not true because this can be removed by an appropriate field redefinition of zeta minus. So this term actually does not belong in the EFT. You can just remove it by a field redefinition of this form. So really, the leading order term is actually one where you have a zeta plus to some n powers, but also at the very least one zeta minus. So as we see, even before we've imposed any symmetries, we can only have marginal terms possible in the EFT. So the worst time dependence that you can get for any operator that you calculate is a logarithmic time dependence. And this is actually a result that people have known for a while. This is Weinberg's classic result that divergences, time dependence in the IR for de Sitter is at most logarithmic. It's not worse than that. So there are no power law time divergences in de Sitter. So it's nice that the EFT reproduces this in this fashion. So now we've understood how to power count different terms and understand RG. So now we want to impose our symmetries as well so that we can constrain the action. So zeta, as we earlier said, has this symmetry of dilatation where if you rescale x, that's kind of similar to shifting zeta by a constant. So this is the dilatation symmetry or the shift symmetry due to dilatation. And because zeta is zeta plus zeta minus, and zeta minus was time dependent, so zeta minus does not absorb this symmetry, but zeta plus absorbs this shift symmetry. So in terms of our EFT fields, zeta plus is shift symmetric, while zeta minus does not transform um, under scaling of x. So this means because zeta plus should satisfy this symmetry here, it actually means that we cannot have a pure power of zeta plus times zeta minus. Rather, all terms have to come with spatial or time derivatives on zeta plus. And since we need two spatial derivatives, this will, at the very least, give us a order k over ah square extra suppression. So the worst divergence after imposing symmetries is also not going to be logarithmic. Every term should be irrelevant. So really, in the IR, all terms are suppressed by order lambda square. This argument is not exactly complete. This is because our action is gauge fixed. So we can actually have non-local terms that are allowed as well. For instance, when Maldacena calculated non-Gaussianity, he had this term in the action. So the derivatives can go in the denominator as well, which is a slight subtlety. So if this goes into the denominator, you can have power counting that is boosted and some terms can start becoming relevant again. But so I will not go into this in very details, but the idea is that these non-local terms, you can still show that using symmetries, these non-local terms are still suppressed, actually. And in the interest of time, I'll probably skip over this. Um, but right, so you can take into account these non-local terms, and you'll still see that at the very least, all terms in the IR are k tau or k over ah squared suppressed. So, so doing this analysis, we can actually finally claim that zeta plus really does not generate any time dependence in the theory without having to resort to any loop calculations. That's just how the structure of the theory and the symmetries are built. It just imposes this constraint. So now that we've made an entire theory or did this entire EFT stuff to understand the time dependence of zeta, can we also say more things about the IR? I just said that all the interactions are irrelevant. So is the IR completely trivial? Is there no interesting dynamics? So the EFT, what does the EFT predict? So remember that we had two questions at the beginning. One was if we put these derivatives of zeta, can they give rise to any time dependence? And the other was how to understand these infinite self-contractions of e to the zeta. So we've already shown that there can't be any time dependence, which is from the EFT. But now we want to understand these e to the zeta terms. So even though we said that zeta plus itself does not have any time dependence because there are no relevant terms, composite operators actually do generate time dependence. This is because zeta plus has scaling dimension 0. So powers of zeta plus can mix. Zeta minus had scaling dimension 3, so that could not mix, but any nth power of zeta plus can mix with itself and with the identity. So this also tells us that e to the zeta plus also can generate time dependence in general. So to do that, we just expand e to the zeta plus in its power series, and we can consider various self-contractions between all of this, and we can regulate the divergences. So a dumb thing, for instance, that we know is zeta plus square uh, will have time dependence in general because of stochastic inflation. So it would have a random walk kind of a time divergence. So these time divergences do exist, and once we reabsorb or regulate all of these divergences, what we actually get is a nice result. So the various big contractions of e to the zeta plus, after we contract all of this, it actually renormalizes again into e to the zeta plus with a counter term. And so e to the zeta plus acquires an anomalous scaling dimension, and it's an eigenvector under Rg. It does not mix with any other operator. And so that's a nice result. And the the coefficients gamma n, which tell us how e to the zeta plus runs under time derivatives, they are just the cumulants of the probability distribution of zeta at any one point. So gamma 2, for instance, which came from contracting zeta plus square, it just tells us the standard deviation, and the higher gamma n's encode the higher moments of the probability distribution. So e to the zeta plus, really, you want to renormalize this with some prefactor z times e to the zeta. Great. So this is a nice result because we learned that e to the zeta plus renormalizes into itself. So this means that zeta plus and hence zeta still retains all of its symmetries in the IR. Uh, and this is another nice way to see that quantum loops cannot change the symmetries of zeta, and hence it cannot change the original intuition, which told us that zeta should be time independent outside the horizon. Also, the time dependence of e to the zeta plus is a very physical thing that we should expect. it actually encodes the time dependence of the volume of the universe at the end of inflation. So, what do I mean by that? The idea is that remember that in our gauge, we had chosen inflation to end at the same time everywhere. The inflaton was given by phi equals phi of t, and we'd pushed all the perturbations into the metric. Um, so Gij was given by a square e to the 2 zeta. So the time dependence of e to the zeta is just telling us that a of t itself, or this spatial metric, it gets the additional statistical time dependence. And because this tells us the volume of the universe, it just tells us that the volume of the universe gets this additional time dependence. And this fact, it just encodes the quantum nature of the perturbations, which give rise to the statistical nature of the volume of reheating surface. Great. So yeah, we have used the EFT techniques to understand the effects of loops in the IR and how to regulate loops in the soft limit. Um, I wanted to also talk about the effects of loops in the UV and how we can use representation to regulate loops in the full theory. But I think in the interest of time, maybe I will skip that. But right, so just to give a quick overview, Melon is a scheme that we've introduced in our paper, where we do loops in the full theory from the sub-horizon to the super-horizon modes, and it regulates loops in a manifestly Demireg way. Um, but okay, I think I will skip the Melon representation part. Um, but right, so what we learn is that we can use EFTs, and using symmetries and power counting, we can show that zeta is time independent to all orders. And we do this without resorting to diagrammatics. We also study the IR effects of loops. So the loops actually do give some effects, and we show that the time dependence that we get is the space-time volume that gets some time dependence. And the last thing that we did not get the chance to talk about is just the Mellon representation and a way to do loops in the full theory, which can also show us how zeta is time independent directly. And it also tells us how to do loop calculations for different correlators if people are interested in that. Um, but yeah, I think